NASA is returning astronauts on the moon in mid-2027 with its Artemis program. The cutting-edge technologies included on board will help solve dangerous problems that arise with long-term stays on the lunar surface. One such problem focuses on repelling lunar regolith. The top layer of rock on the moon is made of sharp, abrasive particles that cling together and can cause irritation in the skin and the lungs. With extended stays on the moon, lunar dust could pose an extreme risk to the astronauts. To combat this, NASA, in partnership with GT Clever, has developed the Electrodynamic Dust Shield, or EDS system. EDS repels lunar dust using alternating electrical current passing through its flexible membrane. However, the team behind EDS has little data on its properties in bending conditions. This is where Team Joint Discovery comes in. We are tasked with creating an automatic bending machine to bend the EDS system so that the team behind it can gather useful data on its properties. GT Clever will then use this data to better understand the efficiency of EDS and its feasibility in future lunar missions. Team JD must adhere to three main consumer-driven requirements for this project. First, the mechanical rig must bend the EDS according to a known standard, and for the final design, Team Joint Discovery followed IEC standard titled Mechanical Bending Test of a Printed Conductive Layer on an Insulating Substrate. This standard is extremely applicable to the final design. The standard highlights the bend radii that the substrate should adhere to, as well as the overall design for the mounting plates. Overall, the standard will prove to be extremely useful in designing the final product. Second, the system must bend the EDS up to 180 degrees completely autonomously. Adjusting the stroke length and bending radius are vital to testing a variety of loading conditions in the EDS. Lastly, the rig must fit and operate inside of one of Georgia Tech's ultra-high vacuum chambers. The vacuum environment helps experimenters mimic the lack of atmosphere on the moon and to test the system in realistic scenarios. The vacuum chamber also houses a mechanism to drop synthetic lunar dust so that they can test the EDS's ability to repel while in high vacuum. Our final system must fit inside this cramped enclosure. Additionally, the vacuum environment means that only certain materials and products can be used. This is because hard materials like metals do not have a dangerous off-gassing effect that other soft materials like plastics do. Plus, any feed-throughs into the chamber must be mounted to custom-rated vacuum flanges found on the outside of the chamber. This includes the vacuum-rated linear actuators that will be used in the final design of our bending rig. From these requirements, Team Joint Discovery developed a final prototype to use in the chamber. The system uses two linear actuators to serve 2 degrees of motion, very similar to the standard mentioned previously. One actuator will move the mounting platform horizontally to control the bend radius of the EDS. The other actuator moves vertically to perform the bending motion on the EDS. Together, they allow the team to autonomously bend the EDS system for thousands of cycles. The mounting plates themselves are designed with a wire mesh to allow lunar dust to fall through without getting trapped between the EDS and the metal plate. From testing, a vacuum-rated fiberglass mesh was selected because it was found to be the material least attracted to the lunar regolith. Additionally, each mounting plate includes a clamping mechanism for the wire mesh as well as for the EDS itself. These can be tightened outside of the vacuum chamber using standard hand tools. Overall, the design can be easily machined from vacuum-rated aluminum so that it can be used in a low-pressure environment. From these CAD files, the team was able to develop a high-fidelity prototype and perform a bending test inside the actual vacuum chamber. The test employed a combination of 3D printed and machined parts for use as a prototype. Watch the bending rig in action now. Overall, the test was extremely successful. It proved that the system can function and physically fit together in the chamber. The next steps for the system before use under high vacuum includes machining every part from aluminum or some other metal. Furthermore, for prototyping, Team JD used a non-vacuum rated linear actuator to induce bending. However, for the final product, an expensive vacuum-rated motor must be swapped in place. Overall, our system will be able to bend the EDS system in the vacuum chamber so that GT Clever and by part NASA can gain usable data for future space companies and spacecraft to use on their lunar missions.